Welcome to Spring LIB.
In this problem, we are given these two half reactions, and we want to use the information of the standard reduction potentials given for both of these half reactions in order to determine what the solubility constant Ksp is for cadmium sulfide. When we are talking about a solubility constant for a given solid, in this case CDS, the reaction for the solubility of this in an aqueous solution is breaking it up into its ions. So that's CD2 plus aqueous plus S2 minus aqueous. And for this reaction, the equilibrium constant or solubility constant Ksp is equal to the concentration of CD2 plus aqueous ions times the concentration of S2 minus aqueous ions. We write this out the way we write out any other equilibrium constant expression. CD2 plus and S2 minus are the two aqueous species that we can write in terms of their concentrations. They are both products, so they both go on the numerator of the solubility constant expression. And on the reactant side of this reversible reaction, we have solid cadmium, which does not factor into our expression for Ksp. And so the denominator of the Ksp expression would just be 1. And so when CD2 plus and S2 minus are both at their equilibrium concentrations, and they're multiplied together based on this one-to-one stoichiometry, then the value that comes out to is the equilibrium constant Ksp. So we need to rearrange the given half reactions in order to resemble this solubility reaction. And then once we have that, we can calculate based on the standard reduction potentials what the value is of the overall cell potential, which we can use in the Nernst equation to help us determine what the value of the equilibrium constant K, and in this case, a solubility constant Ksp is for CDS. So these are the two half reactions again that we are given, and we can see that in order to rearrange them, in order to get that solubility reaction, we have to manipulate them in this way. We keep the first reaction as it was, CDS plus 2 electrons going to CD plus S2 minus. It had a given reduction potential of negative 1.21 at standard conditions, and we had to reverse the second reaction. So now we are oxidizing solid cadmium into cadmium 2 plus in aqueous solution. So we reverse the sign of that standard reduction potential since we are now oxidizing cadmium. And so we can see that when we reverse the second reaction, we can cancel off 2 electrons and cadmium solid appears on each side. And so we are left with cadmium solid, that's CDS solid, goes to CD2 plus aqueous plus S2 minus aqueous. And that matches what we said is the solubility reaction for CDS. And now when we add those potentials together, we see that the overall cell potential at standard conditions comes out to negative 0.81 volts. And now we know from the Nernst equation that the cell potential at non-standard conditions is equal to the cell potential at standard conditions minus 0.0591 over n times log of Q. But we are trying to find K. And at K, we know we are at equilibrium. And at equilibrium, we know that the value for the cell potential E is 0. And we have a value for the cell potential at standard conditions, so we have everything that we need to solve for K. So at equilibrium, the cell potential is 0. This is equal to the cell potential at standard conditions, which is negative 0.81 volts minus 0.0591 over n. And we cancel that 2 electrons when we combine those equations, times the log of Ksp. So now we have everything that we need to rearrange this equation and solve for KSP. And when we do that, we get a final answer for that value to be about 3.9 times 10 to the power of negative 28.